Hi, everybody. We're starting off with a theorem 5.8, which has three actually theorems in it. The first one is the Cauchy-Schwarz inequality, that the absolute value of the inner product of u and v is less than or equal to the magnitude of u times the magnitude of v, or the length of u times the length of v, whatever word you want to use for it. Now, this is extraordinarily important, this inequality, because we had we had this idea of cosine theta, and cosine theta we know is always between -1 and +1. But how do I know this fraction is between -1 and +1? Well, the Cauchy-Schwarz inequality tells you that the numerator, which is the inner product of u and v, is less than or equal to the denominator, u times v, or length of u times length of v. So without the Cauchy-Schwarz inequality, the whole concept of cosine theta, the whole concept, which couldn't exist, and if there's no cosine theta, then there's no theta, and we'll be sad. The next super important thing is called the triangle inequality. See, it says that the length of u plus v is less than or equal to the length of u plus the length of v, because length of u, length of v is like two sides of a triangle, and then u plus v is the other side of the triangle, that length. So it's that's why they call it the triangle inequality. And finally, we have a generalized version of Pythagorean theorem, that u plus v squared is equal to u squared plus v squared if and only if u and v are orthogonal. And remember, orthogonal means that their dot product equals 0, but in this case, we're talking about inner products, so their inner product equals 0. And that's kind of cool and awesome. Well, let's look at an example of the Cauchy-Schwarz inequality. How about from a fun topic that we love so much? What do we call that again? Calculus. It's been a while. I know you all took calculus because, well, I just know it. Anyway, so here we have f of x equals 1 and g of x equals x. These are two functions, and they're in the vector space C0, 1. So this is all the continuous functions from 0 to 1 in the closed interval. And they have the inner product defined as in example 5. Oh, I didn't want that. We still in the air. And the inner product is going to be that the inner product of f and g is going to be the integral from 0 to 1 of the regular product f of x times g of x. And in this case, it's just going to be the integral from 0 to 1 of x, because it's 1 times x, and that's equal to x squared over 2, value between 1 and 0, and that gives me 1/2. There you go. Now, for the right side of the inequality, we want to show this guy right here. So f, the length of f squared, that's going to be equal to the inner product of f with itself, and that winds up being the integral of 1, which is just x from 0 to 1, which is 1. And g squared, or the length of g squared, is going to be the integral of g times g, which is x times x, which becomes x cubed over 3, a value between 1 and 0, and that's just 1/3. So the product of the multiplication product of length f times length g, that's going to be equal to 1 times 1/3 square root. Where did this big square root come from? Well, because 1 and 1/3 are not f and g, they're f squared and g squared. So f times g is going to be the square root of 1 times, or I say length f times length g is going to be square root of 1 times 1/3, which is 1 over square root of 2, which is square root of 3, which is approximately 0.577, and 0.577 is greater than 1/2, because 1/2, as you know, is 0.500. So we see that an example that this Cauchy-Schwarz inequality actually held up. Yay! Concept of work. This is a very fascinating and interesting and important topic. Okay, Now I'm going to do something called orthogonal projections. An orthogonal projection in an inner space is, well, let's say U and V are both vectors in R2. And so assuming that V is a non-zero vector, then U can be orthogonally projected onto V. And this projection, we call it projection of U onto V, or the projection onto V of U, whichever way you want to say it. And now this projection onto V of U is going to be some scalar, it's going to be some scalar multiple of V. Just to show you like an idea, a picture of it a little bit. So here's my vector U, and this is my vector V, goes up here. And what I'm doing is I'm drawing from this point, from the tip of this vector, I'm dropping a perpendicular to this other vector. So projection onto V of U is this black arrow right here, but the entire V goes all the way up to here where it says 3, 4. And that's what a projection is. Now I could have projected V onto U, and it would be something like that. It would wind up hitting it over there somewhere. It's also possible, it's really possible that the projection is not necessarily always going to be smaller. It's possible the projection could want to be bigger, depending on, anything is possible. Anyway, that's what we're talking about, orthogonal projections. And this is, by the way, something, if you, again, this is something, if you take Calc 3, some of you may have taken Calc 3 already, some of you are going to take Calc 3, you'll see this idea of orthogonal projections of vectors. They do that a lot in Calc 3 and R2 and R3, and well, you'll get there. And if you're taking Calc 3, you know what I'm talking about. Anyways, if A is greater than 0, meaning it's positive, then cosine theta is greater than 0, and the length of this projection is going to be the length of AV, which is absolute value A times length of V, which is A, which in our case is just plain A, because we said A is positive, but A times V, that's just U, because because we said that the projection of U onto V is A times V, and so A times the length of V is going to be the length of U times cosine theta. And this is significant because, whoops. I just want to show you where this cosine theta came from. If theta is this angle between these two vectors, cosine theta is adjacent, which is projection onto V of U, divided by hypotenuse, which is length of U. So if I take the length of, now A times the length of V is the length of the projection. Okay, and that's the adjacent. So we're saying that the adjacent is equal to the hypotenuse times cosine theta, and that's always true from trigonometry. In fact, if I would divide by the absolute value of U, I would get the adjacent divided by the hypotenuse is equal to the cosine of the angle. And we're talking about this angle right there, this little theta guy right there. Alrighty. Anyways, let's moving right on. So absolute value to theta. Now, what do we do here? We just inserted a V on top and on bottom, so we haven't changed anything. But we know that UV cosine theta, that's the dot product U dot V. We learned that was how we define cosine theta. That's how we learned cosine theta, and so on and so forth. We sort of like proved it in like R2 and R3, and then we sort of extended and defined it in other places. So now, what does this mean? This means that A is equal to U dot V over length of V squared, because if I have A times length of V is equal to U dot V over length of V again. So I just divide both sides here. I divide by length of V, bring it down here. So I get A is equal to U dot V over length of V squared. And that's equal to U dot V over V dot V. So the projection onto V of U is U dot V over V dot V times V. Where did that V come from? Because that's the AV. That's the AV. So and the A A is u dot v over, all we're doing is we're just replacing the A. So if A, now that's all if A is positive. If A is negative, then the orthogonal projection of u onto v can be found with the same formula, because that's trigonometry, works in different quadrants and so forth. I mean, it'll work. So, and you're going to have theta is going to be obtuse, and the projection is going to be on the other side of v, but it's still going to work. Now, let's use this formula, and you could do that. That's something you could show easily with trigonometry and so forth. So let's take a look here. So in R2, your orthogonal projection of 4,2 onto 3,4, which is what this diagram over here, 5.12, that's what that diagram is. That's the projection v onto u of u dot v over v dot v, but u dot v is 4,2 dot 3,4, and v dot v is 34.34, and then times the vector 34. So now this fraction is going to be a plane scalar, plane number over a plane number, but it's this 3.4 is going to stay as a vector. Anyway, this is 25 because it's 9 plus 16, and this is 20 because it's 12 plus 8. You can figure that out, and then we're going to multiply that by the vector 3,4, and we get 12 over 5, 16 over 5, and that is the orthogonal projection. So, which means at that point right there, the tip of that projected vector is 12 fifths, 16 fifths, and that's pretty awesome. So again, so the definition of an orthogonal projection, if u and v be vectors in inner product space and v is not zero, then the orthogonal projection of u onto v is given by projection onto v of u over inner product uv over inner product vv times the vector v. Now again, this is an extension. This is because we just showed this with with trigonometry and R2, but we could be now talking about any vector space and any inner product space. So it's a different again, it's more abstract. But let's find an orthogonal projection in R3. So we're going to use the Euclidean inner product in R3, which means a good old-fashioned, dot product, and to find the orthogonal projection of u, which is 624, onto v, which is 120. So this is a vector out in space. It goes out here somewhere, and that's another vector out in space, which goes over here, was 120 over here, and we want to find that projection. And well, we're going to see it's going to want to be bigger, but we'll see in a second. So u dot v is 10, because I can just do the multiple. It's going to be 6 plus 4. And v dot v is going to be 1 plus 4, which is 5. So the orthogonal, that's it. You see, that's what I love about that. Dot products is so easy to do. It's so easy to take. So easy to figure out a dot product. That's what's awesome about it. Anyway, the projection onto v of u is going to be u dot v, which is 10, over v dot v, which is 5, times the vector v, which is 120, the guy right there, which is winds up being 240, which is out here. If you notice, 240, wow, it's actually double. It's interesting. It's precise. It's interesting because it's precisely double the original vector, which happens, just one of those things. Now, let's look at now, in example 10, I'm just taking these two vectors out. So we see that that u minus projection of u. So the u is this guy right here, which was 6, 2, 4, and that was what we had on the previous page. And projection of u was 2, 4, 0. So u minus that u minus projection of u winds up being 4, -2, 4, which is this basically this red perpendicular guy right there. And of course, it is perpendicular to v because that's the point. It's orthogonal because we dropped a projection. That's what projection is. So it's going to be orthogonal. But if you notice, this is the shortest distance. So what we're saying here is that of all the points on vector v, the shortest distance to vector u is going to be that point right there, which is the tip of the projection vector. So that's what Theorem 5.9 is basically saying, that the distance from U to the projection of U onto V, notice the distance from U to here, which is this perpendicular red line right there, is going to be less than the distance from U to any other CV, where C is not UV over VV. Because if C is anything else, I'm going to get something that looks like this, and this red line is longer than that red line, and that's basically this fancy theorem 5.9 is basically saying that. Now let's look at an example of it. So, and this is where it gets very awesome. So f of x is 1, g of x is x, and the function's same smack as before. So the inner product of, so we want to use the inner product from which we had in example 5, which is where I'm multiplying the two functions inside this integral. And we want to find an orthogonal projection of f onto v, which is kind of wild. Okay, well, we know that the product of f and g is 1/2. We did that already. The product of g with itself is 1/3. We did that already. So the orthogonal projection of f onto g is going to be 1/2 divided by 1/3 times the vector g, which in this case is the function g, which is just x. So it's 1/2 over 1/3 times x, which is 3/2 x. And that, my friends, is awesome. And this concludes section 5.2. Bye, guys. See you next time.